Good afternoon, everyone. I welcome you to CS Katha Barta, a talk series where we invite academics and professionals to deliver their talks. Our guest for today's talk is Konduri Aditya. He is an assistant professor in Department of Computational and Data Sciences at IISc Bangalore, where he leads the Flame Laboratory. His research interests are in computational fluid dynamics, turbulent combustion and propulsion, high performance computing, and scientific machine learning. He received his PhD in aerospace engineering from Texas A&M University. Prior to joining IISc, he was a postdoctoral researcher at Sandia National Laboratories, USA. I welcome you, Dr. Konduri Aditya, to CS Kathavarta and request you to take over the virtual stage.
Yes, thank you very much. Firstly, let me thank Professor Subhankar Mishra for inviting me for this lecture. And today I'll be talking about scalable methods for flow solvers application to combustion. Particularly, this work is a very generic talk in the sense that it can be applied for any partial differential equation set. However, I restrict my analysis to fluid flows. So let me proceed. So I direct the Flame Lab at the Indian Institute of Science, Bangalore. We work at the intersection of flow physics, numerical methods, HPC, and data science. And in terms of technology, right, we develop a multi-scale multi-physics solver that uses high-performance computing-centric numerical methods, integrates them along with scientific machine learnings, and develop simulation algorithms and workflows that can scale on really large supercomputers. And in doing so, we develop solvers to solve some of the key challenges in turbulent flow physics applied to combustion, high-speed aerodynamics, and environmental flows. So here is the outline of my talk. I'll start with some motivation on some of the work that we are doing. This is in the context of combustion simulations. Then I'll present two new concepts that we have developed in our lab. The first is the asynchronous computing method. The second is a dimensional reduction technique based on higher order analysis of PCA. And finally, I'll end with some conclusions. So, just to give you a brief motivation, here I give a broad overview on scientific computing. The images that you see on this slide are computer generated by solving a set of governing equations, which in this case are the Navier-Stokes equations along with the conservation of energy and species. So typically, the set of partial differential equations are discretized into an algebraic form using some numerical method. Then these algebraic equations are coded up into a solver and simulations are performed. Once you perform simulations, you get data associated with the flow field, using which we perform some analysis and get some insights into the fundamental flow physics. So now let me tell you what happens when you bring in high performance computing platforms. You have these two additional boxes in the bottom that interact with the scientific computing workflow. With large supercomputers, we are now able to do simulations that are of billions of grid points. And when we perform these simulations, we get really large amounts of data. Currently, we are getting one checkpoint that is of the order of 25 terabytes, and in future, it might go into petabytes. Obviously, this large volume of data cannot be analyzed right fully using traditional methods. So here we want to use machine learning and AI to detect some patterns, predict some anomalies, or create reduced order models for engineering design. And in doing so, the AI models have to work in parallel, which again interacts with the HPC in a distributed data fashion. So with this broad overview, let me give you some examples of combustion simulations that have been recently performed. On the left side, you see a direct numerical simulation of a diesel engine, and this simulation was performed with 3 billion grid points in space. And at each grid point, the solution was obtained by solving 40 partial differential equations corresponding to 40 scalars. Likewise, on the right-hand side, this is one of the state-of-the-art simulations of a gas turbine combustor, where 2 billion grid points were used. And again, at each grid point, there are 15 scalars that were solved. And finally, one of the latest simulation in a decarbonization fuel, ammonia. this had about 35 billion grid points, and there were 25 scalars that were solved at each grid point. This shows the scale of these simulations where you have billions of grid points, and at each grid point you solve about somewhere from 15 to 40 partial differential equations. So this paradigm is called direct numerical simulations. Again, as I said earlier, we solve the governing equations. These are conservation of mass, momentum, and energy. And for non-reacting flows, these are five equations in a three-dimensional space. And in direct numerical simulations, you typically resolve all the dynamically relevant scales both in space and time. That's what makes these computations expensive. Just to understand this, let's consider this bright patch on the right side. When we want to perform these simulations, we want to obviously resolve this bright patch. Additionally, there are smaller and smaller structures within this bright patch, right? We need to resolve those high frequency modes as well. So this is where the mesh requirement comes into picture. And for current state of the art direct numerical simulations, we use about billion grid points and integrate the solution for million time steps forward in time. And when you have a reacting flow, like in the case of combustion simulations, we have additionally the solution of conservation of species, where the number of equations go up to all the way to 100 partial differential equations for a mildly complex fuel. Obviously, these demand massive computations and they're performed on massively parallel supercomputers. Just to understand the parallel computing paradigm, here I take a simple domain of the size that you see on the screen, and let's say it takes a time t to compute the solution in this domain if you run it on a single processor or a single core. When we do the same solution by distributing this entire domain into two different processing elements, now the compute time reduces by t over 2. However, the data has to propagate across different processors, which is achieved through the communication between the two subdomains, and the associated communication time is C2. Going forward, if we use four different processing elements, the compute time goes over as T over 4. However, the number of communications increase and the associated communication time is C4. Ideally, the compute time T should scale as 1 over P as we increase the number of processors, which is the factor that you see on the left side of this column. However, in practice, you have this associated communication time. And if I show on the right hand side the strong scaling plot, where we increase the number of processors and measure the time taken to compute per time step of the solution. Ideally, based on this scaling law, it should follow this dashed line. But what we find in actual measurements are these red stars, where you see that as we increase the number of processors, it deviates from the ideal scaling line. And this is mainly coming from the communications like C2 and C4, and these increase as we increase the number of processors. Therefore, at extreme scale, compute time reduces in strong scaling, and communication time increases, and after a certain point, the communication time overwhelms compute time, and this is where the codes start scaling poorly. So let me skip this slide. Let me now talk about the solver that was used to showcase some of the earlier combustion simulations. This code is called S3D. This code uses the simple finite difference schemes of 8th order accuracy and uses a 10th order filter to remove some of the spurious oscillations. And the code uses 6-stage 4th order Runge-Kutta time scheme, and the chemistry is evaluated using a ChemChin library. The parallel form of this code initially was built using MPI with non-blocking communications, where there is a good amount of overlap between computations and communications achieved as a part of initial optimization. When the GPUs came into picture, for example, using on this Titan machine at Oak Ridge National Lab, these were ported to GPUs using OpenACC in its initial version. Later, more recently, this code has been ported to a dynamic runtime model called Legion, and a higher level model called Regent was also used to express in a way that domain scientists can really appreciate and work with this code. So with these kind of optimizations, let's see how this code scales. The standard vanilla Fortran version, right, scales at the bottom with the increasing number of nodes. The number of grid points computed per second are reported on the y-axis, and what you see is that as you increase the number of nodes, roughly the number of grid points that you compute per second is about 18,000 to 16,000 at the extreme scale. However, when we go to the Legion S3D code, which is fully optimized for GPUs, you see a significant amount of increase in the number of grid points that you can compute per second. However, when we increase the number of nodes, you deviate from the ideal scaling line, which is this flat blue line, and see a gap. This gap appears because of communication overheads. So what next, right? Can we do anything to optimize this further? So again, just to repeat, this code was fully optimized in terms of computations. So the GPU or hardware was fully utilized. All the kernels were optimized based on CUDA, and it achieved about 4x increase at a lower number of nodes. However, when scaled on the Summit supercomputer with 4,000 nodes, you see a significant degradation in the performance, and this is attributed to the communication overheads. Essentially, at extreme scale, communication becomes the bottleneck in solver development. So the focus of our research in my group is on looking at some of these optimizations to improve scalability. First, in terms of numerical method, we are working on asynchronous computing methods that address the communication bottleneck issue. Additionally, beyond finite difference, we are also looking at the discontinuous Galerkin method that can achieve high arithmetic intensity and allow the codes to scale much better. In terms of chemistry, which form the significant component of our compute cost, we are looking at low dimensional manifolds based on machine learning methods to reduce their compute cost. Further, in the simulation workflow context, we are using machine learning based accelerations to generate quick initial conditions from desktop level LES simulations, and also looking at data driven discretization methods to achieve better numerical properties and reduce the compute time. So now let me move on to the first part of the contributed work. It is called the asynchronous computing method. This work has been done in collaboration with my students and the group at Texas A&M and ETH Zurich. I'd also like to acknowledge the funding from MOE STARS, ANRF CRG, and the compute time provided at SERC IISc and the Oak Ridge facility. So to quickly review a simple finite difference method, in this slide, we solve the simple 1D time-dependent heat equation. On the left, you have the temporal derivative. On the right, you have the spatial derivative. This differential equation can be converted into algebraic equation using the finite difference schemes. For time, we use a forward Euler method. For space, we use a second order central difference method. So in this algebraic equation, all the black terms are known. The only unknown is the blue term that we want to use to advance the solution in time at different grid points. This equation is solved on the one-dimensional grid that you see at the bottom of the equation, where any generic point, black color I, the solution at this point can be advanced using the finite difference equation. When we solve the same equation in a parallel setting, we decompose this one-dimensional domain into two halves. For example, if we are using two processors, the first processing element computes the first half, the second processing element computes the second half. All the black points for which the data is needed to compute the finite difference equation, it is available within the memory of the processing element. However, if you go to the processing element boundary, for example, this point I, which is at the gray color point, the value I minus 1 is not being computed in its memory. It is actually being computed in processing element 0. So we need to communicate this value from the left processor to the right processor by using a halo or a buffer point. Okay, and this communication happens in two steps. First, we initiate communication. If you are familiar with MPI protocols, we use MPI I send and I receive. And then to ensure that the communication has finished, we employ a synchronization call. For MPI I send and I receive, it is the MPI wait. Okay, and the way the final difference equation currently operates is that I cannot proceed the computation at this grid point I unless I finish the communication and the synchronization. This is where the communication degradation happens in PDE solvers, and it reduces the scalability at the extreme scale. So in the asynchronous computing method, what we do is we initiate the communication using MPI I send and I receive. However, we do not enforce explicit synchronization of the communication, which means now at this ghost or the buffer point, the latest value need not be at time level n, right? If messages are in transit, the function value here can be n minus 1, n minus 2, and so on. And we call the time level of the latest value available in this buffer to be n tilde. N tilde is equal to n if the communication happens really fast, in which case the function value here is synchronous, or if the communication is slow, it can be any of the previous time levels. Okay, so if we employ this strategy where we initiate the communication, but we do not enforce communication synchronization, which takes up majority of the communication time, it modifies the final difference equation to the one that you see here highlighted. Again, the unknown here is the one in the blue color, and all the others are known. I want you to focus on this red color term where its time level is not at n but at n tilde, and n tilde depends on how fast the messages arrive at the destination processor. In general, these communications can be modeled as a random process. Therefore, n tilde is a random variable. It can take any of the values provided in the set given here. If it is really fast, you have zero time level delay. If it is really slow, you can have a delay which is non-zero. Obviously, this modification to the final difference equation modifies its properties. So in our previous studies, what we have found is these kind of numerical schemes where we relax communication can remain stable and consistent. However, its accuracy is significantly affected. To understand this, we perform a simple set of numerical experiments using the linear advection diffusion equation. The initial condition is signed to x, and as we evolve the solution in time, the wave moves to the right and its amplitude decreases because of the diffusion process. On the right, I show the error plot for the synchronous case, which is the textbook way of doing things, and this error is obtained by comparing with the analytical solution. What you see is the solution is moving to the right, and the error increases as the time evolves. Now we do the same thing in the asynchronous way where we communicate or initiate the communication but do not enforce explicit synchronization of the data. So these solutions are given by the black line. They are in good agreement with the red dashed lines. So in the solution plot, we hardly see any difference between the synchronous and asynchronous solutions. However, on the right side, when we look at the error, now the magnitude of the error has increased by an order of magnitude. And you actually see four sharp peaks at these dash dotted vertical lines that correspond to the processor boundaries. This is where the delays in communication are introduced, and they result in these huge peaks in error. And with time, these peaks propagate into the domain and corrupt the entire solution by amplifying the error. Now the question is, do such schemes provide accurate solution or not? So to understand this further, we increase the grid resolution that closely is associated with the numerical properties, right? And then we also understand what are the other parameters that can affect the numerical properties. In the synchronous case, I can scale the error as a function of grid resolution. However, when you do asynchronously, these additional parameters come into picture that characterize the error. This include the number of stencil points to approximate the spatial derivative, the number of processing elements, and obviously you cannot have infinite delay between two different processing elements. So we we restrict the maximum allowable delay to L time levels, and then given these L time levels, what is the probability of having that particular level K in during the course of the simulation, which in turn depends on the communication performance, the latency of the network, bandwidth, message characteristics, even the kind of MPI implementation that you are using. So to characterize the error, now we have increased the grid resolution and computed the average error in the domain for a second order synchronous scheme where you have always zero time level delay corresponding to P0 equal to 1.0. The error scales with a slope of -2, which represents a second order accurate solution. We do the same thing asynchronously. Now what we observe is as we increase the grid resolution, the error decreases, which is a good thing. That means the solution is stable. And the convergence rate has now reduced from -2 to -1, which means now the solution is only first order accurate in space. And when I go from the green line to the magenta line, I increase the amount of asynchrony that you encounter during the communication. And we observe that the slope doesn't change, which means all these solutions are first order accurate in space. However, the absolute magnitude of the error increases with increasing the amount of asynchrony. Just to summarize, asynchronous schemes are standard schemes used in an asynchronous fashion, provide stable solutions, right, through this plot. However, their accuracy drops from second order to first order. Even if I take a fourth order accurate scheme, as I'll show later, the error drops to first order. To understand this, we did a simple Taylor series expansion and computed the truncation error associated with the numerical scheme. When n tilde is equal to n, which corresponds to zero delay or synchronous computations, the leading order terms are order delta t and order delta x square. However, when we introduce one time level delay, which means n tilde is equal to n minus 1, in addition to these terms, these red color terms that are a function of both delta t and delta x appear in the truncation error. These are the terms that are responsible for the degradation in the accuracy. If I introduce a generic delay k, right, n tilde is equal to n minus k tilde, the k does not alter the exponents of delta t or delta x, but appears as a prefactor in the truncation error, which explains that as I increase the amount of asynchrony, the magnitude of the error increases, and because the k doesn't appear as an exponent, it doesn't change the order of accuracy of the solution. So as I was saying earlier, even if you take a fourth order accurate scheme, right, when you do the same computations asynchronously, the accuracy drops to first order. Overall, in our work, we have showcased that, or we did the analysis and found that the average error scales with the mean delay experienced at all the grid points at the processor boundaries during the course of the simulation. And the error also scales linearly with the number of processors and is first order depicted by the exponent of delta x being 1. Now let's move on. Obviously, we cannot use these kind of first order accurate solutions to do high fidelity direct numerical simulations. So we started developing what are called the asynchrony tolerant numerical schemes. The idea behind these schemes is that we expand the stencil either in space or time only for the points at the processor boundaries. Now, by doing a bit more of compute, we gain a lot in terms of communication. So here is a typical scheme that uses a 5-point stencil in space and a 4-point stencil in time that computes again the second derivative, which is fourth order accurate, right? If you perform this kind of simulations with these kind of schemes, now you see on the right hand side how the error behaves. Again, let me recap. In the previous plot, only the synchronous case gives you a slope of -4. All the asynchronous cases are only first order accurate. Now, if I use the asynchrony tolerant schemes, all the lines are on top of each other with a slope of -4, which means I am not currently waiting for the communication to finish. I will take whatever data is available in the buffer, maybe it is current, maybe it is delayed, and then it can be of different orders of magnitude in terms of delay. But what I find is when you use these asynchrony tolerant schemes, your error is always fourth order accurate and of the same magnitude as the synchronous one. And here we, in this reference, we also showcased how the error scales with different other parameters like the number of processors and the moments of the delays. And we then extended this numerical scheme not just to finite difference but also to discontinuous Galerkin and finite volume methods. Just to quickly illustrate this, here I consider a simple one-dimensional wave equation, and this 1D domain is divided into several non-overlapping elements. The example is given here, and within each element we try to fit a polynomial basis function to obtain the numerical solution. So what we do is we take the solution to be a linear combination of the basis functions, and then we minimize the residual upon substitution of this approximate solution into the governing equation. And this is done in a weighted integral sense, where for the Galerkin method, the weighting functions are same as the basis functions. So again, I'll skip some of this math, and I just want to mention that in the discontinuous Galerkin method, the communication between two different processing elements arises because of the numerical flux computation. In this case, the numerical flux is AU, which is the advection velocity times the function value itself. And at each element interface, you need to compute the numerical flux, that is a single value that maintains consistency and is obtained between the two solutions U minus and U plus. So let me just skip some of these. And so what I want to point out here is this is a fully discrete discontinuous Galerkin equation written in the matrix form. And the dependency of communication is due to the dependency of the solution at the element E on its neighbors E minus 1 and E plus 1. So now if you do the same thing asynchronously, what happens? Let's understand that using this figure. Each of the processors has its respective solutions at the end interface of the element, which is let's say this point. For the element on the left boundary, right, what you find is the solution is available at nth level at U minus, right, in the element E minus 1. However, the UE plus should come from the neighboring element, which is achieved using communication into the ghost nodes. This can be done in the synchronous case and you obtain high order accuracy. However, when we do the same thing asynchronously, we cannot now ensure that the function at the latest time level is available at these ghost nodes. They can be of any time level n tilde, and n tilde can vary across different elements at the processor boundaries. So this modifies our update equations where the asynchrony effects come in both elements E minus 1 and elements E plus 1. So we modify this stencil accordingly, and then we use what are called asynchrony tolerant numerical fluxes. And now we compare the solution for a nonlinear Burger's equation between the synchronous and asynchronous solutions. And we see that the solutions upon using the asynchrony tolerant schemes or numerical fluxes are on top of each other. To quantify the error, we use a second degree polynomial solution, which is expected to give third order accuracy or a slope of -3, and we observe the same both for the synchronous and asynchronous cases. The bottom line here is that we do a bit more of computation at the processor boundaries, but we gain significantly by either minimizing the communication or by removing the communication for few time steps overall. To understand what are the gains of this method, we performed strong scaling plots for a simple 3D turbulence problem. This code was parallelized using hybrid OpenMP MPI, and this was scaled up to 12,000 cores. We used two different implementations of MPI. The first one that uses MPI I send and I receive, denoted by the two-sided communication calls. The other one, we have also used the one-sided communication calls that are part of remote memory access implementation. And what we see is the graph that you see on the slide. As we increase the number of nodes, the synchronous computations plateau out, given by these purple lines, and you see a scaling at 10,024 cores, right? That almost plateaus out. However, when we do the same thing asynchronously, given by the orange and yellow lines, you see that the scaling has improved. At the extreme scale, right, we find that relative to the synchronous case, we are about 2.2x much faster. And a few more things that I want to point out from this plot. Each of the simulations was executed 20 times, and the execution times are plotted as the error bars, or the variance in the execution time is plotted as the error bars. What you observe is across the 20 runs, there is a huge variability in the execution time for the synchronous cases. And this mainly appears because of the network traffic or the system noise associated. Okay, however, the amount of asynchrony that we can tolerate in these simulations has allowed us to reduce this variability on the network traffic or the operating system noise, and has made our method robust towards some of these performance issues. To understand why this is happening, we did a detailed profiling of the codes. On the left side, I show you the decomposition of the total execution time into computation time and communication time. As we increase the number of processors, the computation time given by the red line drops nearly linearly. However, the communication time remains nearly flat. And after a certain point, the communication time overwhelms the computation time, and you see the degradation in the scalability of the server. When we do the same thing asynchronously, while the computation time reduces, the asynchronous communication time also has reduced and has been quite minimal. This has led to the improved scalability given by the purple line. We also use this method on GPUs. We have scaled on the Summit supercomputer and ran this simulation up to 6,000 GPUs. And what we found is at the extreme scale, we get about 75% speed up, right? And this was done by one of my first master's students. And we show that the method works equally well on both CPUs as well as GPUs. Finally, to understand what's happening in GPUs, which is very compute intensive and lacks or scales poorly due to data movement, we observe that across different algorithms, the synchronous communication avoiding algorithm and synchronization avoiding algorithm, the compute time remains given by the red lines, red bars is nearly the same. However, we are able to significantly reduce the communication time across different node counts. So this has led to the improved performance for us on GPUs. And we have tested these on turbulence problems in three-dimensional space. We have looked at short Schottky problems that have that result in very large gradients and are signature of hyperbolic systems. We have developed low storage Rangakuta methods where you do not have to communicate across RK stages. We also analyzed the errors in the spectral space and applied this to more realistic problems like the flow transition over the aircraft airfoil, right? So now let me just summarize where we are in terms of the asynchronous computing method. We started this work during my PhD, where we first introduced the concept of asynchrony for the finite difference schemes. We developed the asynchrony tolerant finite difference schemes, and then we showcased the scalability of these solvers on simple compressible turbulent flows. And after joining IISc, we were able to validate these for reacting flows. We developed asynchrony tolerant Vino schemes. We also developed these low storage Gakuta schemes where you do not need communication across stages. And finally, we also extended this concept to discontinuous Galerkian and finite volume methods where we have developed the asynchrony tolerant fluxes. We are currently doing a performance evaluation of this asynchronous DG method using the DEAL2 library that scales really well on large supercomputers. And we are developing 80 Vino limiters for capturing shock waves and detonation waves. And we are also looking at implementation of these on dynamic runtime models like Legion and Regent. So with this, I will take a quick pause and I would like to know if there are any questions from the audience.
Yeah, Dr. Aditya, on the slide number 29, you
Yes,
showed that, like, let's say till 1000, like on the right-hand side, like
yes,
till 1024, now there is a
yes,
point where they match. So
yes,
is
yes.
it like asynchronous is not scalable beyond 1024 points again, and we have to think something more? So that is an open problem in that sense?
Yes, yes, that is true, right? Depending on the characteristics of the network, the latency of packing of the messages, the API implementation itself on how it is doing the buffering and so on, right? Eventually, the communication time plateaus out,
Okay,
right? And beyond which things will stop scaling further.
okay, okay,
Right. But when compared to synchronous case, now we are able to extend the scalability at least 3 or 4 times the problem size or the core count that we are using earlier.
okay,
Yes.
okay, okay. Thanks, thanks.
Yeah.
Yeah.
Any other questions from anyone else?
No other hands are raised. Yes.
Okay, so now let me move on to the second part of the talk that focuses on reducing the communication for reacting flow solvers. We use standard dimensional reduction techniques like PCA. Additionally, we have developed our own version of PCA called the co-curtosis PCA that is based on the fourth moment tensor. This work was mainly done by my PhD student Shivasai in collaboration with Hemant Kolla from Sandia National Labs. This work is supported by the NSM project and the core research grant from SERB. So let me just quickly show you this slide. Don't get intimidated. There are too many equations, but what I want to give the message is that we solve the governing equations that conserve the mass, momentum, and energy. And when we are looking at the species concentrations, we also solve for the species conservation, which on the right hand side has the term Qj that computes the progress of different reactions or that encapsulates the production rates of each species, which in turn depends on what is called an Arrhenius model to compute the rate constants. And these rate constants involve exponentials, which are expensive to compute when compared to simple finite difference schemes. So the summary is that when you solve reacting flows, you have a large number of equations that arise because of the multi-component species in the fluid flow mixture. And within those, a majority of the time is spent on computing the production rates that contain these exponential functions that are expensive in nature. So, if I want to minimize the compute time for reacting flow solvers, I really want to focus on reducing the number of equations that I solve for the species conservation. To illustrate what I mean by that, if you consider a simple hydrogen combustion system, which you might have studied in high school chemistry, H2 plus O2 gives water, right? This is what we would have studied. However, it doesn't happen this way. In the process of hydrogen oxidation, a lot of intermediates are formed, and a simple mechanism that is widely used contains at least 9 species and 21 reactions, which means I have to solve 9 additional scalar equations to track concentrations of all these 9 species that you see as a part of this table. To further explain this, what we mean by dimensional reduction, let's take a generic reaction where A plus B gives C plus D. So you have two species interacting and giving upon reaction two additional species C and D. If we solve this in a traditional fashion, we need to solve four partial differential equations to track the concentrations of A, B, C, and D. So that means four PDs. And this is turning out to be expensive when you have large number of species. So now what we try to exploit is the fact that when A is getting consumed, B is also getting consumed. And simultaneously, C and D appear. That means there is a strong correlation between the decrease in the concentration of A and concentration of B, and then the increase in the concentration of C and concentration of D. So now the question that we ask is, can we exploit these correlations between the different concentrations and come up with a low dimensional space? For example, R gives P, right? Where we now have to solve only two partial differential equations, right? Now the question is, what are these R and P, right? How do we obtain those? This is a standard dimensionality reduction technique where we are going from a four-dimensional space to a two-dimensional space. And one of the popular techniques is the principal component analysis. To illustrate this, let me orient you to the schematic that you see on the screen. You have the data lying in an x1, x2 space, right? We do an eigen decomposition of the data by constructing the covariance matrix and get the eigenvectors a1 and a2, right? The a1 vector, which is the first principal vector, aligns along the maximum spread or the variance in the data, and the a2 vector is by construction orthogonal to a1. So what we do next in dimensionality reduction is project this data from x1, x2 space to a1, a2 space, and to perform dimensionality reduction, we truncate the higher modes. In this case, a2 mode is truncated and all of this data is projected into a1 space, which means the data that was initially residing on a two-dimensional space is now projected onto a one-dimensional space with errors that are minimized due to the eigenvalue decomposition, and the errors that you incur because of the projection are the normal distance of each point onto the a1 vector. So in the context of chemical kinetics, let's say there are nv number of variables that we want to solve, and there are these equations are solved at ng number of sample spaces, right? What we want to do now is project this nv data into a lower dimensional space that has nq number of chemical species or nq number of mathematically equivalent species, right? So the forward projection of this data is done using the eigenvectors that are part of this matrix AQ. And upon having the data in low dimensional space, we want to solve all of the original equations in this low dimensional space and then finally reconstruct the solution into the high dimensional space. This is the nonlinear reconstruction part, and people typically use artificial neural networks or Gaussian process regression to do this nonlinear mapping. So in the context of autoencoders, we can think of this entire infrastructure as we have the full high dimensional data that is part of the input to the autoencoder, right? The encoding happens, you get the data into the low dimensional latent space. You solve all of your partial differential equations in this low dimensional space and then reconstruct the solution back into the full thermochemical scalar space. So this is the analogy with respect to autoencoders. And what we find is, while PCA has been widely used for different applications, for applications where you have the physics happening in sparsely sampled points, for example, these points here, the projection errors are quite large for these points, and the hypothesis is that PCA may not be the right basis for such problems, right? So we then came up with what is called co-kurtosis PCA. First, I want to understand what kurtosis is, and the reference given here very nicely puts it as kurtosis being a measure of either existing outliers or propensity to produce new outliers, right? And in a multivariate setting, we compute what is called the co-kurtosis tensor, which is an outer product of your data matrices, right? And particularly, we look at the cumulant form of the tensor, where we first construct the fourth moment tensor and subtract the lower order contributions from these. Then we take this four-way tensor and perform higher order SVD, where we first metrize this tensor and then do an SVD. We get the principal values and vectors that correspond to the co-kurtosis or the fourth moment. So now let me plot the vectors from the fourth moment, which are given by these blue lines. The first principal vector is aligned along now the direction where you have these sparsely sampled points that are extreme valued in nature, right? And the second one by construction is orthogonal to the first one. Now, what I do next is I arbitrarily change the location of these extreme valued samples to something else, right? While the second moment vectors or the PCA vectors, the first principal vector is aligned along the maximum direction or variance of majority of the samples. The first principal vector from the co-kurtosis PCA reorients itself to align along the extreme valued samples that are sparsely sampled. The same thing you see on the third plot as well, which means now if I look at the projection of the data points onto the two bases, which are the red solid line and the blue solid line, the summary is this. While the red solid line incurs low projection errors for all the points that are part of the main cloud, the blue ones incur very low error for the extreme valued samples, but may incur large amount of error for these main cloud of points. However, in the context of combustion or whenever extreme events of interest, these are the points where we want to minimize the errors, because our entire dynamics are happening in this area. So what we do next is we use this blue color basis to do the dimensionality reduction. So to achieve this, we have considered a simple test case based on a homogeneous reactor. This reactor is governed by a coupled ordinary differential equations given by the time derivative and the source term. We transform this high dimensional equation into a low dimensional space by multiplying this with the principal vectors matrix, and then we evolve the solution across different thermochemical conditions. So just to understand this methodology, you have your original solution in high dimensional space at the initial condition. We project this into the low dimensional space, and then we compute all these ODE or PDE solutions in this low dimensional space, and then the reconstruction happens through the high dimensional space. By doing this, we gain a lot in terms of the compute time. So we implemented this in two different settings. The first one is the standard ordinary differential equation, where we have to first obtain the training source term for the ODE solvers, which is obtained using an ANN. And in terms of implementation, once the ANN model is trained to predict the source term, we evolve the solution and reconstruct the full solution in the high dimensional space. So if we do this, the actual ground truths or the true solutions are given by these yellow color lines for both PCA and co-kurtosis PCA. And then if we evolve the solutions using the standard ODE solver, the PCA ones incur a large amount of error and do not evolve the solution at all, while the co-kurtosis PCA solutions retain the shape, but there is an offset in the ignition point, which means it is able to integrate the solutions, but there is a mismatch or an offset in terms of how the profiles evolve. This we have tried to understand and found that these errors are because of the propagation of the manifold errors across time steps. And when we minimize these using a new approach called neural ODEs, we were able to significantly reduce these errors. Both PCA and co-kurtosis PCA perform equally well when we use this neural ODE approach. We then reconstructed the original thermochemical scalars that contain the fuel, the intermediate species, and finally the water, temperature, and heat release rate. What we find is, while the PCA incurs some errors at the critical locations which are part of the flame, the co-kurtosis PCA retains all of the shapes quite well and minimizes any errors due to dimensional reduction. We applied this across different conditions and found that the PCA incurs large errors depicted by the red boxes, while co-kurtosis PCA minimizes these errors showing indicated in the green boxes. We applied this to a much larger mechanism that has 88 equations reduced to 10 principal components, and we retain all of the mode shapes as we evolve in time. So to conclude this part of the talk, we identify that chemical reactions happen in a low dimensional manifold, And often these points are sparsely sampled where the chemical dynamics are quite active, and PCA may not be the right choice if you want to capture outlier points. So we defined what is called the co-kurtosis PCA, and we showed that upon coupling with neural ODE solvers can significantly improve the accuracy of the predictions and can significantly reduce the compute time for these partial differential equations by minimizing the number of variables. With this, I would like to summarize my talk. In addition to the problems that I have shown you in this talk, we also work on molecular dynamics frameworks for chemical kinetics. We do simulations of large-scale combustors relevant to scramjets and gas turbine engines. We are also looking at machine learning methods like super resolution and regression methods to predict and accelerate simulations. I would like to thank all my students and collaborators who have been making my journey quite fruitful in terms of research. And I also would like to acknowledge the funding from different sources listed here. With this, here is a summary of my talk. I have presented a broad overview about scalable direct numerical simulations for combustion applications. I have mentioned what are the challenges, and the main challenge comes from communication and computation. And I have developed two different methods to reduce each of these separately. As we go ahead, we are looking at asynchronous discontinuous Galerkin methods being state-of-the-art methods for chemical kinetics based fluid flows, and we use machine learning to accelerate these further. With this, I would like to stop here and happy to take any questions. Thank you very much.